This is lecture 24 of condensed matter physics 1, and we are going to start a new topic today. What you have learned so far is, as far as crystals are concerned, that they have a structure, a well-defined structure, which is a basis of atoms or molecules on a lattice. But everything that we did was static, except for the Debye-Waller factor in X-rays, where we did take into account the motion of atoms. Now, what we want to do is go to dynamics of lattice. So, for the lectures this week, I am going to cover dynamics of atoms in a lattice, or even better, a crystal. And what we mean by that is, given this crystal, which has the atoms sitting at regular positions which are given in an arrangement, how are they moving and what is the effect of their moving about their equilibrium position? And that affects their properties. So, I want to start with discussion of specific heat of non-conducting solids. It behaves in a particular way because of this motion of atoms about equilibrium. And just to remind you why I am calling it not conducting solids, and this is a question I had also asked while covering specific heat of metals, is that when I plot specific heat of metals divided by T versus T square, I get a straight line which behaves like AT plus BT square, and this is for low temperatures. And what we had learned while doing Sommerfeld model is that the AT term, this is not AT, A term, and AT will be CV, CV proportional to AT is due to electrons. This was derived. And at that time, I had asked you a question, how do you know that it is BT cubed? The other term is BT cubed, or that AT is, this is electronic, and where does this come from? So, this we are going to show that CV proportional to T cubed arises from motion of atoms in a crystal. So, this is all experimental background for this, and this is related to motion of atoms about their equilibrium position. So, when we talk about specific heat, let me start with monatomic gases, where you take energy per degree of freedom, because this is precisely how we are going to build things out here also, which comes out to be 1/2 kBt, and then you have in 1 mole Na atoms, where Na is Avogadro number, and therefore, energy as a function of temperature per mole is equal to 3 Na, which is the degree of freedom, times 1/2 kBt. So, this is 3/2 kBt, and this gives you Cv, which is equal to dE dt equals 3/2 Na Kb, which is 3/2 or roughly 12 joules per mole. This is monatomic gases, where the only motion of atoms is translational. So, this is just to remind you how we get specific heat of gases. Now, come to solids. And what do I have in solids? I have these atoms which are not moving freely, they are actually bound at their places, and since they are in equilibrium, the only motion they can perform, slight motion about it, and this you can recall from your classical mechanics, is going to be simple harmonic motion in the first approximation. How does that come about? So, you have an atom at equilibrium. The potential energy about that point R is going to be V at the equilibrium position plus a term proportional to dV dr times R minus R0. Since this is in equilibrium, this term goes to 0, and then you have the second order 1/2 d2V by dr square. This is symbolic, R minus R0 square, plus higher order, and this term is like 1/2 kx square. So, the motion is simple harmonic, and the energy E for each atom is going to be 1/2 k x square plus 1/2 k y square plus 1/2 k z square, which is the potential energy, plus the kinetic energy 1/2 m v x square plus 1/2 m v y square plus 1/2 m v z square. And if you take the thermal average, each quadratic term gives you 1/2 kBt. So, this will come out to be equal to 3 kBt. Notice the difference between this and purely translational motion, where we had 3/2 kBt. In this case, there are two quadratic terms. 1/2 kBt comes from the kinetic energy part in each direction. So, each degree of freedom gives you 1/2 kBt for the kinetic energy, and 1/2 kx square gives you 1/2 kBt for the potential energy. And therefore, for per mole energy as a function of temperature is going to be equal to 3 n Avogadro. kBT equals 3 RT, and CV, which is dE dt at constant phi, is 3 R, roughly 24 joules per mole. So, what you expect is that if I plot CV versus T for only these atoms performing simple harmonic motion, I have taken away the electronic part, it should be a constant, roughly 24 joules per mole. And this is known as Dulong Paret law, that the specific heat of a non-conducting solid is going to be 24 joules per mole. But connect it with what I talked about earlier, that specific heat of a metal, if I plot CV over T versus T square, it goes like a straight line, A plus BT square. I am going to ignore this A part. So, C V goes as BT cubed for non-metallic systems like insulators. So, if I were to plot it again, CV versus T, I have Dulong Paret about 24 joules per mole, and I have the experimental graph which goes to 24 joules, but then goes to 0 as T goes to 0. This is experimental. So, why the difference? And recall, this difference is very much like what we observed in black body. So, just a digression here. Black body radiation. Classical derivation which is Rayleigh Jeans. It says that if you have an electromagnetic field, electromagnetic waves in a cavity, then the number of modes is 8 pi for the frequency nu square over c cubed, including all the polarization. And if you calculate classically, the energy per mode is equal to 3 by 2 kBT, then u nu T comes out to be proportional to nu square kBT. It just keeps going up, which is, if you recall from your earlier courses, is nothing but known as ultraviolet catastrophe. So, with nu it will keep going up. So, if you keep looking at, continue with black body radiation, the radiation actually as a function of nu looks something like this. Classical result is something like this. This is Rayleigh Jeans. So, there seems to be a connection. The way equipartition theorem was giving wrong results for black body radiation, similarly, it is giving wrong results for the specific heat also. By the way, for low frequencies, there is a good match for nu over T going to very small values, Rayleigh genes and experimental curves for black body u nu t match. So, situation seems to be similar out here. If you go to very high temperature, Dulong-Pettit, which is derived from classical theory, matches with experiments, but as you go to low temperatures, there is a deviation. So, the answer to this problem as to why this difference, right. So, I ask this question, why the difference between Dulong-Pettit law and experimental curve. The answer is again quantum theory. And according to quantum theory, what we learned in black body radiation. So, let me go back to black body radiation. The energy is quantized. Energy is quantized, and let us say 0 h cross omega, although it is 1/2 h cross omega, we know that. So, I am just taking reference to be 0, 2 h cross omega and so on. So, if I calculate the energy per oscillator at temperature T, how would I do it? The probability that it has n h cross omega energy is minus n h cross over kBT, proportional to that. Then I multiply by n h cross omega, sum over n equals 0 to infinity, and divide by summation e raised to minus n h cross omega over kBT. This will be the average energy. The average is thermal. So, if you are at temperature T, this is the average energy per oscillator. So, in a cavity where I have electromagnetic waves, each mode of electromagnetic waves has this energy, summation n equals 0 to infinity n h cross omega e raised to minus n h cross omega by kBT divided by summation n equals 0 to infinity e raised to minus n h cross omega divided by kBT. I will let you do this derivation, it is quite easy, and this answer comes out to be h cross omega over e raised to h cross omega over kBT minus 1. What is this? This is equal to the average energy per oscillator, or average energy per mode of EM waves in a cavity. Total energy, therefore, E total is going to be number of modes between nu and d nu. So, E nu equals 8 pi nu square over c cubed, we will see how it comes, and then the average energy, which is h cross omega, or I can write this as h nu over e raised to h nu over kBT minus 1. So, this u nu t is equal to this E total for nu for frequency between nu and nu plus d nu is equal to this will be d nu. 8 pi nu square over c cubed h nu over e raised to h nu over k b t minus 1, and then there is this d nu. So, just for completeness, u nu t is equal to 8 pi nu square over c cubed h nu over e raised to h nu over k b t minus 1. This is Planck's distribution. And this matches perfectly with the experimental curve. What is happening is that since this oscillator, which has energy difference h nu or h cross omega, as temperature goes low, these modes cannot be excited. The upper energy levels are not occupied anymore, so energy really goes down. Whereas, in a classical distribution, everything was continuous. So, no matter how low a temperature it is, some modes are always excited, and that is the difference between quantum and this. And it is this fact that oscillators have quantized energy, and therefore, the energy distribution is, the Planck distribution leads to also explanation of specific heat going to 0 for crystals which are non-metallic and going as T cubed. So, let us do that now. So, what we are going to say is what Einstein said. The energy is quantized not only for EM waves or EM oscillators, but for all oscillators, including mechanical, oscillators. So, in a crystal where I have these atoms which are oscillating about their positions with some frequency omega, I can write that energy of each atom vibrating with frequency omega is going to be equal to h cross omega over e raised to h cross omega over k b t minus 1. And if there are n oscillators, then E as a function of t for these n oscillators is going to be n h cross omega over e raised to h cross omega over k b t minus 1. This is of course under the assumption that all atoms are vibrating with the same frequency. And then you take its derivative with respect to temperature and you get Cv. So, let us see what we have, just recapitulate what we have done. What we have said is that the EM waves have quantized energy and u nu t is given as 8 pi nu square over c cubed times h nu over e raised to h nu over kBt minus 1, which can also be written in terms of omega as 2 omega square over pi c cubed h cross omega over e raised to h cross omega over kBt minus 1, where this term is the number of modes. And recall what we did when we were doing free electron model. There we had counted number of modes. It's exactly in the same manner that we are writing number of modes for EM waves per unit volume, and the second term is average energy per oscillator. In exactly the same manner, what we are saying now is that for vibrating atoms, the average energy per atom is equal to h cross omega over e raised to h cross omega over kBt minus 1, and therefore, E for n atoms is n h cross omega over e raised to h cross omega over kBt minus 1. Two questions here. One, show that summation n h cross omega e raised to minus h cross omega over kBt divided by summation e raised to there is n e raised to minus n h cross omega over kBt is equal to, this is n equals 0 to infinity, h cross omega over e raised to h cross omega over kBt minus 1. And two, what is the density of states assumed in writing ENT as given above. So, these are two questions I like you to think about. So, once we have done that, it is very easy to calculate specific heat. So, given E per mole, for that I will write n Avogadro e raised to h cross omega over, n Avogadro times the average energy per atom, which is h cross omega over e raised to h cross omega bar kBt minus 1. Cv per mole is going to be d by dt of this, which is then equal to Na, you can work it out, Kb h cross omega over kBt whole square e raised to h cross omega over kBt minus, there is no minus here, it will come in the denominator, divided by e raised to h cross omega over kBt minus 1 whole square. That is the Cv. Let me box it. And and let us see its behavior as temperature goes high and temperature goes low. So, if we take T going to infinity, very large, then h cross omega by kBt is very small, goes to 0, and Cv per mole is equal to Na Kb h cross omega over kBt times, I get 1 here, this is square, divided by h cross omega over kBt whole square. So, this comes out to be Na Kb. And for 3 degrees of freedom, instead of Na, I will have 3 Na Cv per mole is equal to 3 N Kb in Avogadro, which is Dulong patent. So, this is fine as you go to high temperatures, giving you the specific heat which is expected from classical formula. This is exactly like black body radiation, matching with the Rayleigh-Jeans formula for nu by T being very small. On the other hand, as T goes to 0, then e raised to h cross omega by kBt is very large, and Cv per mole will be equal to Na Kb h cross omega by kBt whole square e raised to minus h cross omega by kBt, and that you can very easily see goes to 0 as T goes to 0. So, this is the kind of behavior that you are expecting from this formula. This out here is exponential, and this is 24 joules per mole. So, as you go to low temperatures, although the specific heat is not following T cubed, it is still going to 0. So, what that tells you is you are in the right direction. If you take quantum effects into account in that at low temperature, then you cannot excite many modes. Then specific heat, the system cannot take a lot of energy, and therefore, specific heat goes to 0. So, this is known as Einstein's model. What we have just done is Einstein's model of specific heat of insulators. And what we have done in this is each atom is vibrating with the same frequency omega, and E average from quantum mechanical point of view is given as h cross omega over e raised to h cross omega over kBt minus 1 for each atom, and then the rest of the results follow. So, that is the Einstein's model. If each atom was really vibrating with the same frequency, you would get exponentially increasing or exponentially decreasing as T goes to 0 Cv, and then it goes to 24 joules per mole, and this is exponential. I am plotting Cv with respect to T. How do we get T cubed? So, let us explore that further. And this has to do with distribution of frequencies. It is not fixed frequency, it is a distribution of frequencies. So, there is a density of states. D omega, which has a value for each omega. Now, I have already asked you what is a density of states d omega for Einstein's model. Think about it, and here now we are actually going to calculate the density of states. Again, I am going to connect with black body radiation. So, let me connect with black body radiation, and what we had there, that u nu t was equal to 8 pi nu square over c cubed h nu over e raised to h nu over k t minus 1. And I have already told you that this term is related to modes of vibration, and this term is energy per mode. Simple harmonic. That is the approximation we have been making. So, let me just recall how these modes are calculated. So, what we do is that we have omega equals k c for light, and if you go back to how we are doing free electron theory, we have the volume between k and k plus dk, the volume in k space is equal to 4 pi k square dk, and per unit volume the number of modes is equal to 1 over 8 pi cubed. So, the number of modes is going to be between k and k plus dk is equal to 4 pi k square dk times 1 over 8 pi cubed times 2, and this 2 is for 2 polarizations. So, from here I get k square dk over pi square, and k is omega over c. So, this is omega square d omega over c cubed pi square. That is the number of modes. So, you get u, and in nu also I can write this as in terms of nu as nu square times, I get 2 pi from each, 8 pi cubed. So, 8 pi over c cubed d nu. So, I get u nu t equals 8 pi nu square over c cubed times that e t. That is the derivation. Now, just now I realized I may have missed a factor of 2 in going from nu to omega earlier. Please check that. Now, we are going to do exactly the same thing for vibrations in a crystal. Let us see what is happening in a crystal. So, I have this atoms and they are vibrating. So, suppose there is a k like this, k vector. I could have these atoms vibrating like this, what I will call longitudinal, vibrations, or they could be vibrating in perpendicular direction, transverse, vibrations, and there will be 2 of them. So, they are vibrating. Now, we are going to assume certain things about this vibration. What we are developing essentially is what is known as Debye model. It is a model. So, we are going to assume that all vibrations propagate with the same speed, which is going to be Vs, speed of sound. So, as these vibrations go from one place to the other, and we are going to see later how we justify this, they are going to go with the same speed, and we are going to assume that omega equals k Vs. This is exactly like for EM waves, except that C has been replaced by Vs. So, all I got to do is now count the number of modes, multiply by the energy of vibration for each atom, and then we get the answer for the energy. So, total energy. So, now number of modes. In doing so, I am assuming that lambda, the wavelength of these vibrations as they travel along, is much greater than A, that is the spacing. Between atoms. So, I am going to sort of take a continuum model, and therefore, the number of modes between k and k plus dk again is going to be 4 pi k square dk times 1 over 8 pi cubed. No polarization here. Why? Because I am counting each mode separately. Each mode is independent. So, the number of modes between k and dk plus dk is going to be 4 pi k square dk times 1 over 8 pi cubed, which is 1 over 2 pi square omega square d omega over Vs cubed, which can also be written if I write omega equals 2 pi nu which is going to be 4 pi nu square over Vs cube d nu. That is the number of modes. Now, total number of modes for one particular type of vibration is equal to n. All three of them will give you 3n, and therefore, what I am going to have is that in the largest radius of some nu, which I am going to call nu Debye or omega Debye, the number of modes is equal to n in a sphere of radius omega d or nu d. More explicitly, if I do 1 over 2 pi square omega square d omega over Vs cubed 0 to omega d, this is going to be n. So, there is a maximum cutoff frequency up to which the atoms can have vibrations, because beyond that the number of modes will go up and violate the basic counting. So, this gives you basically that 4 pi by 3 omega d cubed over Vs cubed equals n. Is that correct? No, this is not correct. This gives you 1 over 2 pi square omega d cubed over Vs cubed times 3 equals n, or omega d equals 6 pi square n Vs raised to 1/3, or Kd is equal to 6 pi square n raised to 1/3, where n is the number of atoms per unit volume. I have gone through it a little quickly because this is exactly the kind of derivation which I just now did for light, and earlier we have done this derivation for free electrons. Just to connect, I have taken this sphere up to Kd, which is related to omega d or nu d. I have Kd equals 6 pi square n raised to 1/3. Just recall from free electron theory that I had Kf equals 3 pi square n raised to 1/3. The difference arises because this had 2 electrons per K state. Here there is only one mode. So, we have now found what the number of modes are going to be. The total energy for each kind of vibration, longitudinal or transverse, is going to be, I have 4 pi k square dk times 1 over 8 pi cubed is the number of modes. Energy for each mode is h cross omega over e raised to h cross omega over kBt minus 1, and this I am integrating from 0 to Kd. That is for each one of them. I can also write this in terms of omega. This comes out to be 1 over 2 pi square integration 0 to omega d omega square d omega over Vs cubed h cross omega over e raised to h cross omega over kBt minus 1. So, what we have done here is dispersion omega equals Vsk has been used. In Einstein's model, omega had no dispersion. It was fixed. Here what we are saying is that these atoms can vibrate with many different frequencies, with largest frequency being omega d, and omega d is determined by that the maximum or the total number of modes is equal to the number of atoms. If you take number of atoms per unit mole, so whatever answer you get is going to be per unit mole per mole answer. So, this is it, this is the total energy. So, let us calculate this. So, I have E total as a function of temperature, and if I take per unit per mole, it is going to be n Avogadro. This is going to be equal to 1 over 2 pi square Vs cubed. Then I have 0 to omega d omega square d omega h cross omega over e raised to h cross omega over kBt minus 1. Take x equals h cross omega over kBt, then you can write this E for Na t equals 1 over 2 pi square Vs cubed integral 0 to x d. Outside I get kB t raised to 4 x cubed dx over e raised to x minus 1, where xd is equal to h cross omega d over kBt, and omega t is determined by number of atoms. Now, let us take two limits, t going to infinity. As t goes to infinity, x d goes to almost 0, very small. E raised to x minus 1 goes to x, and therefore, you get E equals kB t raised to 4 over 2 pi square Vs cubed times 0 to x d x square dx. And this is equal to n kB t, where n, since we are doing in terms of the number of atoms per unit volume, n is going to be equal to number of atoms per unit volume. Okay, omega. So, let me just make a note, omega d is related to n. If you want to do it for per mole, then you just write Na, right. So, this is what n comes out to be. For 3 degrees of freedom, remember when I was doing this I did only for one kind of vibration, E would come out to be 3n kBt and Cv equals 3R per mole. So, Dulong-Pettit. So, we are in the right direction. Now, let us go to 0 degrees. If I take T going to 0, I am going to get E temperature T for all vibrations. I will multiply by 3 right away, is equal to 3 times one over 2 pi square V sound cube integration. As T goes to 0, the upper limit will go to infinity. Then I get x cubed dx over e raised to x minus 1, and there was this kb t raised to 4. So, this is equal to some constant times t raised to 4. Cv, which is proportional to or which is equal to dE dt at constant volume, is going to be proportional to T cubed. So, now with this dispersion of omega being taken into account, for large temperature I still get 24 joules, and as you go towards 0, this shows T cube behavior. And this is because of dispersion. So, if you take this special dispersion into account, omega equals k Vs, which is true for lambda being much greater than A. This is like sound wave, Cv t tending to 0 is proportional to T cubed, and Cv t tending to infinity is Dulong-Pettit. And all this is taking quantum mechanical picture. So, thing that becomes clear is that vibrations at this level, at microscopic level, have to be treated quantum mechanically, and with that everything falls in place. And if you take the dispersion to be sound like or light like with speed of sound replacing speed of light, you get T cube behavior. If dispersion is something else, you will get slightly different behavior, but with this in Debye model you get T cube behavior. If you take omega to be dispersionless, you get a exponentially decaying Cv as T goes to 0. So, everything falls in place. So, let me now conclude this lecture by stating that number 1, experimental specific heat goes to 0 as T goes to 0. This is a quantum mechanical effect. So, in lattice vibrations, I got to take this quantum mechanical thing into account, and you will see its consequences as we go further. Then, if omega k is taken to be dispersionless, then Cv t tending to 0 is proportional to e raised to minus h cross omega over kb t. And if omega k is taken to be V sound times k, which is Debye model, then there is a maximum frequency omega d, which is known as Debye frequency, up to which atoms vibrate. And in that case, Cv is proportional to T cube as T goes to 0. Thank you.